Okay, well, I got cut off talking about acid and base neutralization reactions, but I'm going to back up a little bit and talk about this one more time. This is a strong acid, hydrochloric acid, reacting with sodium hydroxide, a strong base. So when we write out the complete ionic equation, everything is busted up into ions except for water, because it's a covalent molecule. We only break up our strong electrolytes into ions, and water is a non-electrolyte on its own. So when we go to cancel out the spectator ions that didn't do anything in the course of the reaction, we see that in this instance, everything was a spectator except for the elements that make up water. So the chlorine ion was a spectator, the sodium ion was a spectator, and so in our net ionic equation, this is sweet pea by the way, in our net ionic equation we're simply going to have H and OH making water. Now if you're thinking, wow, these are going to be easy, this is only true of strong acids reacting with strong bases. Once you throw the weak ones in, it gets a little bit more complicated, but a strong acid, strong base reaction will simply be H and OH making water. Now, this is an example of one that will be a little bit more complicated. The hydrochloric acid here is, of course, a strong acid, but magnesium hydroxide is not one of those soluble hydroxides, so it's not a strong base. It's a weak base. So we'll do this one in class. I don't even want to try to talk through that one. Now, another kind of acid-base reaction involves a base that is not a hydroxide. The base instead is a carbonate. So anytime you pour acid on a carbonate, which you've probably all done if you've mixed vinegar and baking soda. Baking soda is sodium hydrogen carbonate, and vinegar is acetic acid. Both of those are weak. That's a weak acid and a weak base. You've seen what it does. It fizzes. Okay, so if you pour acid on a carbonate, you get salt and water, just like in any other acid-base reaction, but you also get CO2 bubbles. So this occurs with carbonate and hydrogen carbonate. So here's the chalk with the acid. And it occurs in some other situations too. Depending on what the base is, you might get carbon dioxide as a product, or you might get sulfur dioxide, which stinks, so we won't be doing one of those in a lab. Alright, so here is the one we were talking about on the previous slide, the calcium carbonate and hydrochloric acid making salt and water and CO2 bubbles. Here's another example of baking soda, sodium hydrogen carbonate, and hydrobromic acid, another strong acid, making sodium bromide, salt, and carbon dioxide, and there's a water hiding behind my little screen there. Another one is strontium sulfite. That is where we'll get the stinky sulfur dioxide gas. If you mix strontium sulfite with hydroiodic acid, which is a strong acid, you will get a strontium iodide salt, sulfur dioxide gas bubbles, and of course water. So if you notice I'm calling things a salt besides just sodium chloride. A salt is a soluble ionic compound that is produced by the reaction of an acid with a base. So a salt can really be a lot of different things, not just sodium chloride. Okay, here's yet another gas-forming reaction that's even stinkier. Sodium sulfide will act as a base here and accept a proton or accept an H+, and then sulfuric acid, which we know is a strong acid. If you mix those two together, you get the sodium sulfate salt, and instead of water, you get hydrogen sulfide bubbles, hydrogen sulfide gas that smell like rotten eggs. All right, so here's some sample questions. By analogy to examples already given, predict what gas forms when sodium sulfite is treated with hydrochloric acid. So if we poured acid on that, what would it do? Okay, it would be actually an acid-base reaction, but we would get a little something extra. We would get a gas, sulfur dioxide. All right, these are ones that we're going to do in class that involve writing the net ionic equation for different acid-base reactions with weak acids and weak bases. So they look a little different when you write them out. Well, I guess I'll walk through it now. we've got acetic acid mixing with barium hydroxide. Barium hydroxide is a strong base because it is soluble. Notice it's got the AQ after it. But acetic acid is one of our weak acids. So we're going to get some kind of salt, barium acetate here, and water. It gets weird when we go to write the ionic equations. Here, first, balance it, of course. Now, remember, you only bust up into ions the substances that are strong electrolytes. Well, since acetic acid is a weak electrolyte, we're not going to break it up into ions. Why? Because in reality, it breaks up a little bit, but not completely. So even though it says AQ after it, we have to realize that it's not completely aqueous. So we will leave it together in the ionic equation. Since the barium hydroxide is strong, we will separate it. And water is a non-electrolyte. It's a molecular compound, so we, of course, don't bust it up. And then the barium acetate, that is completely soluble. All acetates are soluble, so it will be busted up in the complete ionic equation. So because we didn't break apart the acetic acid into ions here, this is going to make our net ionic equation not quite as simple. We're not going to have just H and OH making water. All right, so what looks like it didn't change? Okay, so we had, who are our spectator ions going to be? We had barium being aqueous, and it still is aqueous, so that was a spectator. The hydroxide went from aqueous to being liquid water, so that's not a spectator. We need to include that. The hydrogen went from being aqueous and dissolved in water to being liquid water. Cat hair. It went to being liquid water, so that changed. So that's definitely not a spectator. And then lastly, acetate was aqueous to begin with, and it ended up being aqueous. You can't quite see it behind my little image here. But it wasn't completely disassociated over here, and it is now. So it wasn't a spectator. It did change. All right, so in our final net ionic equation, the only thing we can really leave out was the barium. Everybody else changed in some way. The acetate went from being only slightly soluble to completely aqueous, completely disassociated. The hydrogen ions went into liquid water, and the hydroxide ions went into liquid water. So that's what I mean by it gets a little bit more complicated. You just have to remember, don't break up the weak electrolytes in your ionic equations. And even though they started out aqueous and ended aqueous, you don't get to call them spectators because they did change. They went from only being slightly soluble to completely soluble. All right, and then here, because everything had a coefficient of 2, they went ahead and reduced it down to just 1s. All right, we'll do that one in class. All right, that is it for acid-base, and I will stop here and pick up on redox in the next video.